So I want to remind you of something that we talked about involving depth first search traversals and breadth first search traversals. So the first thing is that suppose I give you a graph, say something that looks like, so yeah, I'm going to number these 3, 4, and 5. So suppose I give you this this graph. Now, if I were to perform a depth first search traversal on this graph, so remember the process. So suppose that this is the starting vertex. So first I would mark it, and then I look at my incident edges. So I try to run down as far deeply as possible, and whenever I have all more options, I wind back, like my ball of string, like we talked about in our story of Theseus and the Minotaur. So in this case, suppose I consider this incident edge. So remember, we labeled these edges, right? We had what we called forward or discovery edges, which I'm going to label here in blue. So suppose I go this way. And then I'm going to mark this vertex. And then I consider my incident edges from here. Notice that I can go this way. And then I'm going to mark this vertex. I'm going to consider my incident edges. Suppose I go, let's go this way. And then I would mark this vertex. I consider my incident edges. So notice here that the opposing endpoint of this is already marked. So that means that I have a back edge. So I'm not going to go down this way. That makes no sense if I'm trying to process this graph, right? Because I've already been there. I'll be back there eventually. Then I notice this one here. Well, this one I have not gone down yet. And let's mark that vertex. And now let's process my incident edges from here. So notice that this edge here, so keep in mind, it doesn't matter which order you consider them in. This one already has the opposing endpoint marked, so this is a back edge. This one's already marked, so I got a back edge here too. And notice all my incident edges have been processed. So now I'm going to wind back up my string, which remember, what kind of data structure is this underlying representing? A stack, right? So I go back down to 3. Notice that all my incident edges have now been considered. Notice, same thing here. When I reach these ones, they all will be labeled, right? So I could go back this way. The same idea, same idea. Notice that all of the edges and vertices are processed. However, notice something. We said something actually last time, was that these blue edges, the forward or discovery edges, they always form what we called a tree, right? Remember, a tree is an acyclic graph that is connected, right? But furthermore, it isn't just that. If the original graph is connected, it is what we call a spanning tree. So that means it contains all of the vertices of the graph. Now, if the original graph is not connected, then we would call this a spanning forest. So we'd call it a spanning forest. So if you were to, for example, use DFS on the entire graph, and say you had to rerun DFS on a given vertex more than once, so if it's unmarked, so say you run it on 2 unmarked vertices, you know you're going to have 2 connected components, which we'll talk about at some point here. But the point is that it'll contain all the vertices of some connected component. So this is just an assertion, right? I just asserted to you that it takes this form. This is something I've said previously. However, and I must stress that this is also true for breadth first search as well. You can use the same process there as here, with the exception now you're going breadth-wise, so the underlying data structure is it a stack? No, it's a queue, right? So I actually have to prove this for you, that it actually, the discovery or forward edges form a tree. So in particular, it will be the case that it contains no cycles, right? So that's what I want to prove for you, is that it's going to contain no cycles. Because any of these would not contain any cycles. So let's prove this here together. So enough of me just asserting that. Let's actually prove it. So here's a theorem. So theorem. And I assure you that the argument I'm going to present here, it will work regardless of which kind of traversal it is of these two. So DFS or BFS. Furthermore, it will also be the case that this will be what you need to prove a claim like this. So the argument is rather cute. So consider the subgraph T formed by discovery edges, discovery or forward edges, whichever terminology you'd like, via a DFS traversal, or a BFS traversal. So the claim is as follows, that T does not contain any cycles. It's acyclic. So T does not contain any cycles. So you might ask, Dan, how the heck are we going to prove that? Now, we're going to pull up one of my best friends, proof via contradiction. So let me give you the game plan for how this is going to play out. So what we're going to do is we're going to assume that T, remember, in the claim, the blue edge is that's what T is in this one specific example. So I must stress that we don't necessarily know this. We're trying to prove this. So here's the game plan. What we're going to do is we're going to assume that actually it's possible for T to contain a cycle. So once we have that, we're going to see, based on either one of these two algorithms, and I must stress the way we're going to formulate the argument, we're going to try to pick something that both algorithms do. Now, if you're not convinced by the argument I give you just for both of them in the simple way I do it, I encourage you to pick up each one of the graph traversal algorithms and examine it carefully to see that this is indeed the case. So what we're going to do is we're going to see what happens with these two algorithms. We're going to see if the assumption that we make, or presumption, leads us to what we call a contradictory statement, a statement that is always false. So one that's very common of this form is something like if I gave you a statement and say A and not A. You can't have both of these things like that. That statement is never true because it's that A and not A at the same time. And so if you made it that A is true, then not A is false, right? And if A is false, then not A is true. And that means that regardless of which scenario you give me, it's always going to be that it's just a bunch of hooey, right? So here we go. So I'm going to construct an observation in a moment. So let's see what happens carefully. So assume otherwise. So assume otherwise. Then T contains at least one cycle. And I'm going to give this cycle a name. I'll call it C. Now, what kind of edges is the cycle comprised of? It's comprised of forward or discovery edges, right? The same thing, right? That's what it has to be because it's a part of T. A cycle of discovery edges from a DFS or BFS traversal. Right? Now, let's take a very careful look at what this would look like. So we're just going to pretend. Now remember, if our statement is actually not even true, like if this theorem was false, I should be able to present such a graph to you. So there is a cycle somewhere. However, we're going to we're going to go along with the presumption here and suppose that there exists a cycle. Now, do you remember our example here, like when we process this graph? Now remember, the statement has to be true regardless of what the graph looks like. It has to be any undirected graph. So suppose that I have it where, say, when we considered, say, vertex 5, suppose that when we reach vertex 5, we had it where a cycle got formed. Like suppose that there's a cycle like right here. Say this is a blue edge, for example, instead of a red one. Now suppose that we put that there, and all of the other incident edges, so other edges that form the cycle, already are processed. Well, there's something that we can say about this edge. It's a very special edge. So let me describe this edge to you. So consider the last undirected edge E UV. I'm going to use rounded parentheses just to indicate like which order I discovered them in, but I would normally use curly braces here. Consider the last undirected edge E added to C. So for example, in this case, the cycle would comprise this triangle here. So suppose that's the last edge that gets put in, that forms that cycle. Add it to C in T, where, suppose that this is the vertex I reach before to add that edge in. Suppose that's U. Where U, sorry, we'll say where at least U was marked first. Because to add this edge to the cycle, which would be corresponding to labeling it as a discovery edge, I had to get there somehow, right? So that's what U is. Now, the thing is, to get to U, I had to mark it, regardless of which algorithm you use. So in one scenario, if this is DFS, that means that I reached here, and then I mark it first, then I consider my incident edges, right? In BFS, the way it works is that I would have placed U into the queue, and it finally got its turn, but it would have been marked. So now, as V is an endpoint, of some other edge in C, V is marked, right? So for example here, just to illustrate what I'm talking about, this would be V right here. But remember, V is already marked, because remember, this is the last edge I add to the cycle. That means that there's at least one other edge out there that has and comprises the cycle, meaning that there was some other point previously in the algorithm's execution that had to have marked the other endpoint. Do you see where we're going here? Because if you remember the algorithms for DFS and BFS, you would know exactly where we're going with this. So watch this carefully. So now we know that V is in fact marked. By observing this, one, by observing this, instead of saying by observing this, let's say as a consequence. I think that's a much better way of putting this. I always like to encourage you to find ways to lay out your argument carefully. As a consequence, both endpoints of E are marked. But what does that mean then in either algorithm? Is it a discovery or forward edge? Let me walk you through. Remember, suppose that we were at this vertex at that time and we added this, supposing under our assumption that this is in fact a discovery edge. However, we've observed that also this endpoint is also marked. In either algorithm, this would not have been labeled a discovery edge, right? It would have been labeled as a back edge or a cross edge. Of E are marked, implying E is a back, say if we're talking about DFS, or a cross edge if we're talking about BFS, not a discovery edge. Therefore, now, you have to always be careful when you make arguments like this, right? You have to remember back to the algorithms we presented. They will process every one of the edges and vertices in the graph, presuming it's connected. Likewise, we only label edges with two different types. Forward or discovery edges and back edges if we're talking about DFS. In BFS, we label discovery / forward edges and cross edges, right? So notice there's no other options. So that's a very important thing, and it's so important I'm going to put it down here because I must stress that depending on what kind of graph you're playing around with, like right now we're talking about undirected graphs. If we're talking about a different kind of graph, we would need a stronger statement here. Therefore, as the graph traversal labels all edges and are only discovery edges. I'm just going to abbreviate discovery with disc. Discovery edges or back / cross edges, depending on which algorithm you're talking about, or back / cross edges. Cross edges. What does that mean? What does it mean? We've assumed that we have a cycle, right? We've assumed there is a cycle. That means that this edge E exists, right? That edge E exists in this subgraph T, right? Now we've waded through the jungle carefully, and we've come to also the conclusion, as from that presumption, that also edge E isn't in T, right? That's what it means because it is not a discovery edge. So both, it is the case that both E is in T and E is not in T, which this belies our assumption over here. And that means that we have a contradiction. So you can't have both of these things at the exact same time. And that concludes our proof. So a contradiction right here. So we've yielded a contradiction that assures us there are no cycles. Because if there was, I could show you that there is actually, by the way the algorithm constructs T, it is actually going to be the case that whatever that edge would be, like the one that we have, that we would observe to exist, because it actually will exist always, because at some point you have to form the cycle, right? If if you have this in place, which is the presumption you get when you assume there is a cycle, then it has to be that that edge also doesn't exist at the exact same time, which is impossible, right?